Okay, welcome everybody to the talk on graph attention networks.
Welcome everybody to the talk on
So, why graph networks? Why graph neural networks? Well,
What's your name?
oh, sorry. Sorry.
Wait, so you wanted to say a few words about yourself? Yeah.
Oh, okay, sure. Hello everybody. My name is Karim Khairat. I'm a data scientist here at BMO Capital Markets, and I'm going to be presenting graph attention networks. Paper by Bileokovic and the rest, and let's start. So data on graphs, right? Data on graphs is very ubiquitous. It's in a lot of places. For example, things we're familiar with are the TTC over here. Another thing that we're familiar with are social networks. And this graph here represents protein-protein interaction. And what they all have in common is that there's basically a set of vertices or nodes with a set of edges connecting these nodes. And on these nodes, right, you have different features describing the nodes. For example, in social networks, you can have a feature vector describing the person or what he or she likes and so forth. For the TTC network here, you can have the main feature, how much delay is expected and how much delay had been in the past. And for protein-protein interactions, there are many features which I'm not really able to describe because I'm not a biologist. Next slide. So given graphs, right, you can think about many learning tasks on graphs. One example is graph classification. So you're given a graph and you need to classify it, right? Just like in comparison to images, you classify, for example, cats versus dogs. You can also do something similar in graphs, classify the type of graph. And node classification, which we'll be focusing on in this talk, aims to classify every single node in a given graph, right? So what are you given? You're given as input the graph in a form of an adjacency matrix, A over here. And for every single node in the graph, you're given a feature, right? So you have a set of feature vectors. And the output is just the class of each node. So there are different types of learning node classification learning tasks. I'm going to cover two because that's what the authors of the paper used to test their model. First is transductive learning task. So in this task, the learning algorithm is given the complete graph. It's given all the features of all the nodes on the graph, but it's only given part of the labels of each node, right? So you see here, for example, there's blue nodes, green nodes, and there are nodes which have a question mark on them, which the learning algorithm has to learn how to predict. And I need to stress here that the learning algorithm sees all the features in the graph. That's the transductive learning task. Now, this is relatively easy because you have information about labeled nodes within the same graph as the nodes you want to predict. Now, in the inductive learning task, it's a lot harder. Here, the learning algorithm has to learn to detect nodes on graphs that it has not seen before. So you learn on one graph. You learn what is blue, what is green on one graph. And then you get in a completely unknown graph, right? All you're given is the set of feature vectors of each node. And your task is to predict the class of each node, right? This is the node classification class in an inductive learning setting. So now I'm going to talk about the general idea of graph neural networks. So graph neural networks are basically a wide range of algorithms that deploy deep learning on graphs, right? We're not going to cover all of them here, just a particular subset. But what's the general idea? So the general idea is that you're given these input feature vectors for each node, right? And the idea is to compute some hidden representation for each node, and then take that hidden representation, right, and use that in a downstream machine learning algorithm for your problem, be it node classification, graph classification, so forth. Now, as a baseline algorithm to this, you can take the feature vector directly, so you ignore all graph structural information, take the feature vector directly, and try to classify that node. So that's a reasonable baseline, and that's used also in the experiments to test the graph attention network paper. And as I mentioned, many graph neural networks have been developed. A comprehensive survey has been recently published, so you can look at for Wu Zhonggan's paper, recently published 2019. Okay, so this is just like a schema of what I just described. You have an input. Feature vectors on the graph. There are several hidden layers that you compute. The details of what you do in these hidden layers differ from one graph neural network algorithm to another. But the general idea is that you go through several hidden representations, and then you get an output. And then what you do with the output depends on your learning task. So graph convolution networks are a subset of graph neural networks, right? Basically, they try to compute the hidden states in these hidden layers using a sort of convolutional operator. Now you might think, okay, what's so difficult about that? We apply convolutional operators to images all the time. So what's the problem? Well, there are many problems, right? There are many ways to define a graph convolutional layer. Some challenges that you have to think about is that in a graph, in an arbitrary graph, you can have an arbitrary number of, for each node, you can have an arbitrary number of neighboring nodes, right? So some may have 5, some may have 7, some may have 10, right? So you can just fix a filter size and apply it, all right? Another problem, let's say if all the nodes in the graph have 5 neighbors, right? It's still difficult to define a convolution layer on top of that because they're unordered. So in an image, you have the top left, the top right, the bottom left, the bottom right, the right left, and so on. But in a network, the neighboring nodes are unordered, right? So how do you deal with that? Okay, so with this in mind and with the challenges in mind, we want to construct an ideal convolutional operator on a graph. And that was the goal set out by the authors of this paper. So the first important goal is that the number of parameters should be independent of the input. Whether you have a graph of 1,000 nodes or 1 million nodes, right? The convolutional operator has to have a fixed number of parameters. This is very trivial for image convolutions because let's say if you have a 3x3 filter, for every convolution filter, you have 9 fixed parameters. These are 9 parameters. Done, right? But it's a bit tricky to do that with graphs. Another one is it should be localized, right? There are many different kinds of graph neural network algorithms that use global information to compute the convolution, such as spectral methods. But in convolutional neural networks, the aim is to have a localized filter. So preferably to use nodes that are 1 or 2 edges away from a particular node. And coming back to the point of unordered nodes, you need to give an arbitrary weight to each neighboring node in a neighborhood, right, when you apply. And that's a bit tricky. This is where the attention part comes into play in this paper, the attention part of the graph attention networks. And we'll see how they solve this problem. And note that conventional convolutional layers satisfy all these requirements trivially because you're dealing with structured structural domain. But for graphs, we'll see how this was solved by the authors. Sure.
Arbitrary weights given to different neighbors.
That's a very good question. So remember, this is the neighbors of a node are unordered, right? So how do you decide to give one weight to a node and not to another, right? Or a different weight, right? And you don't have any sense of ordering in a normal convolution network layer, right? You have the relative distance between each pixel, right? But here you don't have that information. The only information, however, I mean, implicitly, you have information about the relative distance to the pixel, right? That's some kind of information that you implicitly forget, right? Whether the node is +1 to the left or -1 to the right, right? In graph neural networks, the analogous thing is that you use the feature vectors themselves, right? To decide what weight to give each node, right? And that makes them more general than doing something naive, like just taking the weighted average of the neighboring nodes. And they solve this problem using the self-attention mechanism, which I will get to.
Can I add some point?
Sure.
So imagine if I want to give you like an analogy. Imagine that you have a social network and then people interacting, right? And you want to infer some information from the people that are, the person, for example, that you're trying to study is interacting, right? So there are a lot of irrelevant information, the task you want to do on that person. But when you have this like similar shared weight with all of the nodes, imagine that he's close friend with one person, has a lot of interaction, and going through the features of that person would provide you a lot of good information. And imagine he has just had one mention with other person who is just a random talk or a special topic, right? So if you want to give it some weight, isn't it better that you give it like different weights rather than just one weight? So that's the intention. What it tries to do is essentially doing the same thing. Given the content, I'm sorry, just a minute. Given the content, you want to provide this weights with some kind of, you want to weight the content and what the intention is. That's the overall view.
Any other questions? Okay, so we go on. So this was basically just the context. Now we get to graph attention networks. But first, we start with what is a graph convolutional layer, right? So graph convolution layer, as I've been saying, is just a building block of the complete graph convolutional network. Okay? So as I said, every node in the graph has a feature vector, right? At the start, it's the input that is provided. Maybe at the center of the network, it's one of the hidden states, right? So every convolution layer deals with an input and an output, right? So the input are the feature vectors at each node, and the output are also feature vectors at each node, but they may have different dimensions. For example, here I showed the input has 3-dimensional feature vectors, and here they have 2-dimensional feature vector, right? So a convolution operator consists of mainly 2 steps. One is an aggregation steps. How do you combine or weight the neighboring nodes together and bring it in to compute the next hidden state? And the other one is you need to apply. Yes.
I just want to know which kind of feature here it is of the node. It is the edge of the node with its near neighbor, or it will be the property of the neighbor of the node itself features.
Okay, thank you for that question. That's a good question. So first, you asked what are the feature vectors, right? What do they represent? Do they represent the structure properties of a node, okay, or something else? So first, you can do both. So one feature, for example, of the vector could be the degree of the node. That could be a feature. But the rest of the features could be problem specific. So for example, if you have graph of Wikipedia articles and how they're linked, right? Every single node, right, can have a feature vector which basically summarizes the content of that article, right? If you have protein-protein interaction graph, you can have every feature vector representing properties of every protein, and so on and so forth. So it's generic what you put in these feature vectors, right? You can also put structure information, yeah? But in general, yeah, it's just a vector that can represent anything. Okay. All right. So the two steps back to the convolution operator, two steps involve. One is aggregation, and two is a nonlinear operation on them. So a complete graph convolution network consists of multiple steps. I have to mention here that, okay, just, okay, so come again. So basically, this is just showing the locality of a convolutional layer operation. So basically here you had the feature vector in the blue node here. It combined, it aggregated the neighboring nodes together, passed it through a convolution layer, and output only one feature vector for that node, right? This is not in all convolutional layers. Some also take features from the neighbor of neighbors, right? But here in the graph attention network, they only took the neighboring nodes, okay? Just distance of one, graph distance of one. Okay, and then you do that for all the other nodes, right? And then you repeat this process for how many layers you want in your architecture, such as here. So you have the input graph with your input features. You have this graph convolutional layer, right? That basically consists of aggregation, some linear transformation, some nonlinearity. And you do this k times, multiple times. Okay, I shouldn't use k because there's k for something else, but you just use it multiple times. And you have an output, okay? And then the output is also a set of feature vectors, one for each node. Then you can use that output, for example, pass it through a softmax function or a sigmoid activation function for your multi-class classification problem or multi-label classification problem. Okay. Yeah.
So the edges are there that they're not, they don't have weights or like features themselves, do they?
That's an excellent question. So in general, you can define something that uses weights of an edge if the edge has some property, right? But the only feature that they're using from the graph are the fact that they are neighboring. That's it. So the only part where the graph structure is invoked here is basically that they're neighbors to each other. Okay.
We have this undirected, unweighted graphs, right?
Yes, and this test is. Okay, the question was, do you have in the graphs that we're dealing with here, is it undirected and weighted? Yeah, and unweighted. Yes, so the edges here are undirected, unweighted. Right? Okay. So any other questions before I move on? Yes.
It doesn't, if I'm understanding it correctly, it doesn't seem like it would be such a stretch to just add any features related to the edges to whatever features you're incorporating from the nodes that happens to be one jump away, right? Like, is there something else there?
Okay, so the question is, it wouldn't be difficult to add edge features into this operation. Yeah, and I agree. So it's not, I mean, you'll have to define a way to how to incorporate the edge properties into the mix, because the edge properties can also be multidimensional, right? But yes, so it's local. I mean, you can define. I'm not familiar with how you would do that, but
You're including properties coming from each of the neighboring nodes, right?
yes.
So it seems like it would just be another feature. That
Sure.
would
All right. Yes, you can do the same thing with. You mean you can do the same thing, but instead of nodes, you do with edges, right? And then maybe, yeah, that's true. Yeah. Sure. Any other questions?
Oh, sorry. Yeah, no, sorry, my bad. I was just trying to understand your question a bit more. Are you saying that for the feature vectors, since they're taking in the structure of the nodes, you're saying that could you not add on or append
Like
on?
literally is another feature associated with that node is like something describing the edge between your target node and that other node that is connected to it.
Yeah,
Right.
it sounds like just an addition. Yeah, just like an addition.
I guess
Like not as a new.
I guess it's possible, but it complicated the network in a different way because I mean, see, if you have two nodes connect to one node here, so if you look at this node as feature associated to node 1, it has a different half of feature connected to the edge. And if you have another node, right? If you're looking at node 2 and then you have a different features. So coming from that neighbor node. So in a way, like you have, I mean, it's possible, but I guess it's more technical, and I don't know. I'm not sure if I conveyed correctly.
So what do you want to put on the edge, actually?
Actually, we can keep this for the discussion.
Yeah, I may also just not be understanding something, but I can ask more later.
All right. So next. So now let's take a step into the author's mind and try to come up with this convolution layer on our own. So first thing you would try is just do the average for every node. Just take the neighboring node features and average them together, right? That's a convolution, right? Where are the learning parameters here? None, right? That's the first step. Second step, less naive convolution. You first multiply each feature vector, neighboring feature vector, by a weight matrix, W, like you do in any neural network setting, and then you average them together. So now you introduce some learning parameter, okay? Something a bit better. On top of doing that, you also incorporate the graph structure to a certain extent by including the information about the degree of every node. And the degree of every node is simply the number of neighbors each node has. And this was the paper by Kipf and Welling, 2017, which was presented by Parham, I guess 1 month ago? Less than a month ago. All right. And now, graph attention networks. So instead of just combining them either uniformly, combining the neighboring node features either uniformly, or by incorporating some graph structure, you incorporate the feature vectors themselves in order to compute the weights that you're going to use to aggregate the neighboring node features. So once again, you take the neighboring node vectors, right? You look at them, you compute some metric out of them that tells you which weight would you use in an averaging operation. So we'll go now into detail on how this works. So some setting to be formal, right? You have the input feature of a convolutional layer, h, h1, hi to hn, where n is the number of nodes in your graph. You have the output feature for each convolutional layer, h prime. And you have an aggregation step, which is basically the weight matrix times the input feature. Yes, sorry.
Output and input features is the same. All of them are in here, or you can just maybe compress the input feature maybe into a smaller features.
Okay, so the question was the dimension of the feature vector. Is it constant or not? Excellent question. Sorry, I forgot to mention. The dimensions can be different, right? and the dimension of the input is f, and the output is f prime. So you do that. You change the dimension primarily by multiplying it by a weight matrix, right, which has the dimension f prime times f, right? And that's the first step over here, w times h, right? So that changes the dimension of your feature vector. And then you combine it by some weighted average, with weights alpha here. And then after that, apply a nonlinearity, and you're done, and you get to the next level. Now the main question here is, how do you compute alpha, right? That's basically the meat of the topic in this paper. Self-attention head. So how do you compute alpha? Which are the weights in how you're going to aggregate the neighboring node features together? So you take, for every edge, right, for every edge on the graph, you have two neighboring nodes for that edge. You take these edges, you multiply it by the weight matrix W, and then you take the result of that and you concatenate it. And that's right over here, right? And then you take a dot product of that by a vector called A for attention, which has a dimension 2 times f prime, yeah, right? Because it's dot product is applying a dot product on the concatenation of these two output vectors, okay? And remember, A here is some parameter that needs to be learned, okay? And then after that, you apply nonlinearity. The authors used Leakey ReLU, but you could use others. And you get some value Eij, right? So that's for every edge, all right? Now you go to every node, and every node you look at the neighboring Eij's, right? And you normalize them by using a softmax function. And that's all to it. That's it. That's the meat, right? So easier said than done, but that's how you get the weights, right, for every node. Yeah.
So can I see the A just as a parameterization of the alphas, or how do I interpret that variable A?
That's a good question. I haven't thought about that.
Can you repeat the question?
So how do I interpret that variable A? Can I interpret it as a parameterization of the alphas?
So the question was, how can you interpret the parameter A here, the vector A, the attention vector? So in a sense, it does determine, right, your alpha ultimately, because it's in the pipeline to compute alpha. But about interpretability, I'm not sure.
Yeah. Doesn't have to be a deep reason.
Yeah.
So I say, like, you can start with just. Sorry, I'm looking this way because I'm looking at the mark that's picking me up. So you can just start with alpha and say, oh, that's my attention, just learn it. Yeah. But it doesn't have linearities and non-linearities, and it's not using the weights that you have. In order to have those, usually in any attention mechanism, you start with the weights and the hidden states, and a parameter A, and then you get to your alpha after a few nonlinearities, and also you want to make sure you pass it through a softmax, so it's a probability.
Yes.
It seems like you have to introduce some notion of a sequence or like ordering across the nodes, the neighboring nodes.
Okay, the question was, it seems that we have to introduce a notion of sequence. Okay, and I mean, my answer to that is no, because it doesn't matter which order, right? All right, so when you concatenate, for example, is that the question? Okay, so in the concatenation, the source node, I mean the center node in which you're doing the convolution is the first one, right? And the neighboring is always the second one that you're concatenating to. So in a sense, there's an ordering, but outward from the central node. And then the rest is you average them, so it doesn't matter which order they are.
So the order comes from the structure. of the graph, you know. So you have this node and you want to get the local structure, right? So the ordering is essentially which are the local nodes, right? So that's the ordering that you can have with the graph.
So just to be clear, like the weight for the I, if the source or the center of the center node, and the J is the neighbor node. So you do that for every neighbor node for node I.
Yes.
And then you apply the non-linearity. They choose the leaky loop.
Yeah. And before that, of course, multiplied by the dot producted by the attention.
I don't know if this is a stupid question, but how is that related to the equation in the previous slide?
Yeah, so the equation on the previous slide is this one, the aggregation.
Yes.
So all this is just to that, should I repeat the question? Yeah. So how is this related to what was on the previous slide? So on the previous slide, we had this equation, right? Which is how you aggregate the neighboring node features, right, together. And it had a parameter alpha ij. And how do you compute alpha ij is by going through this process. Yes, that's a good question. So remember in the requirements, we said that the parameters has... Oh, sorry. What was the question again?
That's a good point.
A is shared among all of them.
So the question is, the attention vector here, A, is it shared across the network? And yes, it is. I mean, that's the idea of specifying this definition of a convolution, is to have a fixed number of parameters, right? And that was one of their goals, right? To have a fixed number of parameters independent of the number of nodes in a graph. So yes, so this is shared. So A, for every layer, for every convolutional layer, it has a separate A, right? And that's universal, right? Then we'll come to that soon, but instead of having only one attention vector per layer, you can have multi. So it's like multi-head attention, similar to that. Similar to how you have multiple filters in one layer of a convolution neural network. So any other questions?
Are you assuming directionality now on the edges, or would you like flip them to have non-directional graphs too? So on your graph,
yes,
the edges look like directional, right?
All right. So this the question is, am I assuming the directionality on a graph? So it's undirected or directed, the graph, based on this diagram. So sorry for any misunderstanding, but this diagram is just a schematic on how to compute alpha ij. It's not actually a graph. So these are the feature vectors of WHI, right? What you get here, 4 and 4, and just this is just telling you how combine them schematically.
If this application of what they're going to for GAT, is it on a directed graph or an undirected graph? Is that what you,
No, I think
or just this specifically?
That we discussed before, but I was confused about this, so it's clear now.
I think I just might clarify some people's questions around this A. But in the paper, it happens to mention that A is a single layer feed-forward neural network parameterized by this A vector. So that's what you could think of this schematic as.
Right.
Hold on. No. So A, you can see A as a vector, right? On the edge?
Yeah. So A is a single layer feed-forward neural network parameterized by a weight vector A, element of the real numbers, the cardinality of 2f prime. So that's the
So if you said E is a feed-forward network, yes, I guess. Oh, A and the first equation, leaky value. Yeah.
This one. All right. Okay. So now that we have alpha ij that's computed using one of this attention head, You can also do the same thing with multiple attention heads. So now you have multiple attention vectors, multiple weight vectors. You do that, and you have two options now. How do you combine the result of all these operations? One is that you can either concatenate them, like shown here. So this is the concatenation operator. If you have k attention heads, you concatenate the output of k of these operations. And in the paper, the authors use this in the intermediate layers. For the final layer, before the classification problem, they used an average instead. And that's about, just briefly about the multiple attention heads. Right.
Hyperparameter, or it's just like a fixed number?
No, yes, that's a good point. Can k here, is k a hyperparameter? Yes. So the authors use different architects for different problems. So k was varied depending on the problem.
But I think so, if I'm not mistaken.
You can correct me on the paper, but I believe that they chose arbitrary k's, correct? I think they chose
3?
Yeah, they chose k equals 3 and then k equals 2, depending on if it's transductive or inductive learning, I believe. When they were doing the comparison, the benchmarking, which you'll get into, I believe that's what they did. Yeah. But yes, to your point, I believe it is. You can definitely treat it as a hyperparameter.
Based on the problem?
Yeah, I believe so. I strongly believe so. Yeah. Because I think we all, when we were discussing it earlier on the paper, I think we were all coming to that same observation. Yeah.
Actually, when they get into inductive learning, they use a different K for different layers as well, which is neat. So it's a parameter to the layer itself.
So the architecture of the networks that are used in the experiments will be shown. I'll get to that in the next slide. Okay. So before we take a break, want to just comment about the scaling of this graph attention network. So a single GAT attention head with input of dimension f and output f prime would scale with the number of vertices times the f prime. So and scale with the number of edges times f prime. If you use k attention heads, the storage and parameter required are simply multiplied by a factor of k because they're independent. And again, because they're independent, during a single layer, the computation of each attention head is in parallel. And yes.
Could you repeat that, like what's happening with the O notation? So the V were the vertices, F and F prime were...
Oh, yes, sorry. V were the vertices, F were the number of input, was the dimension of the input feature that's going into the convolution layer, and F prime was the dimension of the feature going out of the convolutional layer. And E is the number of edges in the graph. Yes.
Stuff, because I think here the feature was maybe more talk about the connections in the network. Otherwise, they cannot concatenate with each other's, because maybe one node has maybe 3 neighbors, maybe another one has 2 or 4 neighbors. The concatenation step may not be performed if they didn't have equal number of the size of features over there.
Okay, so this is which? This is this one, concatenation. Yeah, this.
The previous one. Last.
Okay, so this is the concatenation.
No, not
the previous one.
Previous one. Yeah, the concatenation. Yeah.
But this is always true. This is always on the edge.
The concatenation of the H1 and HI and Hj should be the same dimension, because you concatenate with each other.
Here there's no concatenation.
First one.
Yes.
You're saying the neighbors around. Are you saying so the neighbors around HI and HJ should be the same?
Yeah.
I don't think
I don't know. No.
Those are the number of features, right? Those are the number of features.
Yeah.
Those are the number of features for a node, so that's fixed in every layer.
So the size of H is fixed.
Yeah, the size of H is fixed within a single layer, right? So in a single layer, all nodes in the complete graph has the same dimension of feature vector.
Feature transformation with HI and HJ here.
I mean, this is, you can have multiple EI. Yeah, that's actually maybe a good point to explain again. So again, for every edge, right, you have the neighboring nodes, right? You concatenate the features of these nodes after some linear operation, W. You concatenate them, right? And then you multiply them by the attention vector, right? All right, so here you get a single scalar as an output, okay? So that's EIJ, right? All right, so you can do this whether you have one neighboring node or 10 neighboring nodes or 100 neighboring nodes. Doesn't matter, right? After that, right? After that, what are these numbers used for EIJ? You pass them to a softmax function, which basically makes the sum of EIJ equal to 1, right? Right? So these are weights now. These are alpha ij, right? And then you use the alpha ij to compute a weighted average of the neighboring feature nodes. Again, it doesn't matter if there are 1 neighboring node, 10 neighboring nodes, 100 neighboring nodes. You, at the end, the output is just one feature vector.
So that first equation, leaky relu, inside the parentheses, that vector, that's a dot product, right?
Yeah, that's a dot product.
So it gives you scalar of the two vectors. Yeah.
All right, so yeah, break. Okay, welcome back, everybody. Let's get to the exciting part, the results. So the first task that the authors tested their method on was a transductive learning task. Basically, it was 3 sets of citation networks, right? In a citation network, the nodes represent the papers or the documents, and the edges represent citations between these papers, right? And you have a transductive learning task. Again, just a review. You have the complete graph. They're only partially labeled, right? And you need to find the labels of the unlabeled nodes. And as input, you have the all the features of all the nodes. And a feature, depending on the citation network, right, you can have different classes. So for example, for the Cora data set, you have 7 classes, right? For the architecture of the network, they use 20 nodes per class for training, and 500 nodes for validation, and 1,000 nodes for testing. So the architecture of it was 2 layers of the so-called convolutional operator. The first layer had 8 attention heads with each computing 8 features. So the output of this would be 64 features, right, for the first layer, the output of the first layer. The output of the second layer is C features, where C is the number of classes in the citation network, right? And after that, you have a softmax layer, which basically gives you the class of the paper. And for example, for the core data set, the type of classes, just to have some understanding, could be a paper based on genetic algorithms, a paper based on neural networks, probabilistic methods, and so on and so forth. OK. The authors also apply dropout to layer inputs, as well as to the attention coefficients themselves. So by applying dropout to attention coefficients, it's similar to just doing a random sampling of the neighborhood of a node. superficially, that's what it is. Yes?
Checking, because it says that there's only 20 nodes per class for the training.
Yes.
That seems small.
So for example, for the core data set, you have 140 nodes for training, and the rest is for validation and testing. Okay, sorry, I forgot to repeat the question. The question was, 20 nodes for training seems to be...
I got the question.
Seems to... Okay, sorry.
Only when I let you know then.
Okay. Sorry about that. Yeah. So yes, it might seem a bit small, but remember, this is a transductive learning problem in the sense that the network already sees the features of the unlabeled nodes, right? And in a citation network, if it's an easy problem, right? If 5 papers cite you that are from probabilistic methods and no other paper cites you, this paper is probably about probabilistic methods. So the problem is a bit easier, and you'll see the state-of-the-art result from this paper is not much better than the other papers. Which brings us to the results. Here are the results. So these are the classification accuracies. The first method here as a baseline is a multi-layer perceptron. That's just taking the feature vectors, forgetting about the graph information, right? And the feature vectors, I'm not sure, is it doc to vec, or what did they use as a feature vector for the papers? So it's something representing the paper. I think bag of words, that's what they used.
Yeah, bag of words representation.
Yeah. So the MLP just takes this bag of words representation, applies, neural network, MLP, and you get these results. For Cora, it's a bit better than random guessing. Well, not significantly better, but for PubMed, it does reasonably well. I think PubMed only has 3 classes, so it's a bit easier. For the GCN network of Kipf and Welling, the accuracy is 81%. That's the paper that Parham reviewed 3 weeks ago. 70.3% for sites here and 79% for PubMed. Now for the graph attention networks, it's not a lot better, just 83%, which is just basically 1.5% better. And this is only a couple of percentage points better. And for PubMed, it's identical. So you see here that transductive learning problems are inherently easy. You don't need a lot of learning nodes, right? Because you see the features of all the nodes while learning. You just don't see the labels of the nodes you want to classify. Yes?
What does 64 here means in GCN?
That's a good question. I think if I remember correctly, and facilitators, please correct me if I'm wrong, is that they increase the number of parameters in GCN to match the number of parameters in the GAT, but I'm not entirely sure. So basically, it's to have a fair comparison between the 2 architectures. Yes?
Quick clarification question. So if you move back to the previous slide, you had that 20. I didn't quite get the idea of 20 nodes per class. So is it the input features? Is it
okay, so the citation networks what do you mean exactly? Sorry.
I think I'm asking what's 20 nodes per class?
Okay, 20 nodes per class are used for training the for the graph, the GAT, basically. So for these 20 nodes per class, you have their labels, right? And for the rest, you don't have their labels. Okay. I forgot the details, but the validation nodes are, I think, used for early stopping, and the testing nodes are used for the test. And that's the result here based on the testing nodes. Yes.
So 500 nodes here are the total number of nodes, not per class.
No, it's the total. Yeah, that's the total number. So 20 nodes per class is for training. So it depends on the citation network. It could be 120, 140 nodes, or only 60 for the case of PubMed. but 500 nodes and 1,000 nodes are for the entire NAS. Yeah. And I think the citation network is larger than the sum of all these nodes. It's just that they used the same subset of nodes to classify as the GCN paper, the Kip van Welling paper, in order to compare apples to apples. If I remember correctly, might be mistaken. Okay. So let's go to the harder problem, the inductive learning part. So here, as I said before, the training algorithm just looks at one graph, and it tries to classify nodes on a completely unseen graph. So the training algorithm hasn't seen the structure of the other graph. For testing, the testing graph has not been seen before. Only the features of the nodes in the testing graph are known to the algorithm at the start. So they use for this a protein-protein interaction data set. Here, you can see that they used a lot more training graphs because it's a harder problem. So they needed to use 20 graphs for training, and they only used 2 graphs for validation and 2 graphs for testing. Well, of course, within each of these validation testing graphs, you have a lot of nodes, right? And this is a multi-label, multi-class classification problem, right? Each node has as input 50 features, and they have 120 class. And it's multi-label, so every node can have multiple labels. So the architecture was a 3-layer GAT model. Layers number 1 and 2 used 4 attention heads, computing 256 features each, right? And the last layer had 6 attention heads, computing 121 features each, which is the number of classes. And they averaged them to have a single 121 feature vector. And then they applied the logistic sigmoid activation function in order to do this multi-label classification. And now you see the advantage of this GAT architecture over the other architectures. So this is the micro-averaged F1 score. You see random classification. It has 0.396, very low score. For the MLP, which is basically just taking the input vector and ignoring the graph structure, which is the baseline, it's better than random. So you can get something better than random using that. And then you have different architectures from the GraphSage algorithm. I'm not familiar with the details of GraphSage, but GraphSage mean, for example, is basically taking the average of the neighboring feature vectors, a simple average, or something very close to that. That's GraphSage mean.
Can I insert that?
Yes.
Param presenting GraphSage probably in a few weeks.
April 29th.
April 29th.
Okay, it was also announced that Parham presented the Graph Attention Network. The video is available on our YouTube channel.
Graph convolution.
Sorry, graph convolution.
I'm doing a bad job here.
I just want to advertise that the video of Graph Convolution Networks are available on our website as well as YouTube channel, ACE. Look it up.
Okay, so the best GraphSage had a score of 0.76, and GAT, the authors, had a very impressive score, 97.3%, 0.973 F1 score.
What's the difference between the constant GAT?
GAT, sorry.
Could you repeat the question?
What's the difference between the constant GAT and the GAT? Let me try. I'm not exactly sure. Forgot.
Yeah.
I can fully recall from this, but if I remember, at one point they're kind of having a constant attention to all the nodes around, and the difference was, okay, if we could selectively choose which nodes. Instead of having a constant, it's variable, and that's what they showed the difference. I'll verify it though. It's somewhere along that line.
Okay, and now to the summary of the paper. So,
did you say what PPI was?
Proteins of proteins, right?
Protein-protein interaction.
That's just the
That's
data
the
set.
data set, yeah.
Can I do a plot then?
Not yet. Summary. So,
So did they compare the protein database case with a network that doesn't have attention, like just the regular GC?
right, so the graph sage does not use attention, so that's the comparison. So that was the state of the art at the time of publication. I guess now there are many different, it's been 2 years, so there's been many different developments since then. And I'm not sure about the latest state of the art results.
So there is a graph sage asterisk. Did you also say what that is?
All right. Again, not entirely sure. I think they also modified graph sage in order to have the same, in order to have a fair comparison between the GAT architecture and graph sage. That was the idea behind that.
Yeah, so it says in the paper, further provide as graph sage store, the best result we were able to achieve with graph sage by just modifying its architecture, as you're rightfully saying. This with a 3-layer graph sage LSTM with 512, 726 features computed in each layer and 128 features used for aggregating neighborhoods.
So summary, a convolutional-like layer, not convolution, we'll discuss that in the next slide, that handles different size neighborhoods was developed by the authors. It assigns different weights to different neighbors based on their features, right? It has a fixed number of parameters, that being the attention vector and the weight matrix at every convolutional layer. And it achieved a moderate increase, well, barely any increase for the transductive learning task, but a significant improvement for the inductive learning tasks. And the algorithm itself can be parallelized across all nodes in the graph because the operations are inherently parallel. Some discussion points. First one is something that I guess we all want to know is that how do you compare this architecture with the hundreds of different graph neural network architectures out there, right? So just on top of the list, there are spectral methods that are more traditional ones. There's Node2Vec, there's graph sage, there's etc., mainly etc. And the second point is, I'll go through the points and then I open the floor for discussion. Second point is, why are inductive learning problems harder than transductive? I think we covered that a bit during the presentation. Third one is a tricky one to think about. How does adding multiple layers affect the effectiveness of attention heads, right? Point out that the authors only use 2 layers, not more than that. But I guess they already got impressive results from using 2 to 3 layers in their networks. And the last one is this really convolution? What's the definition of convolution? So, yeah, so I open the floor for discussion.
Is it?
Is it? Yeah.
Did you have a plot? Did you want to say it?
No.
Can I just make a comment here? At the beginning of the presentation, you seem to assume that the graph is bidirectional. But throughout the computation, there's nothing about the graph that says it has to be bidirectional. Actually, the citation data seems to be a directed graph. So, yeah.
That's a good point. I think they treated the citation graph as undirected anyway.
Yeah.
Even though it's a directed graph for obvious reasons.
No, I mean, like all the computation is like directed. You don't see the undirected or bidirectional condition apply anywhere in the computation.
Right.
In the flow of the of the network. That's what I'm saying.
Right.
I mean, the definition of the feature vector, of the attention,
yes,
of the weights are all directed.
They did say in the paper when we were discussing it earlier, they did say that it can be applied to an undirected graph. They do make mention of it.
You know how this is represented is that essentially that the JS matrix that you have, right? So if it is like it's undirected, so what you have, for example, IJ, you would have this one which is noting that they have direction, and also on the JI of this matrix that they are connected. So you will have this one denoting that they're connected. So when it's directed, one of them will be like 0, the other one will be like 1. But then again, you will pass it through this procedure. See my point?
So yes, because it's symmetrical, it shouldn't be directed.
Yes.
Because the input of the adjacent matrix is symmetrical.
Symmetrical, unweighted means bidirectional.
So,
I mean, at least to me, like symmetric and undirected are the same when you don't have weight on the graph, on the edges.
So I guess in here we don't. Why do you use the symmetric? I mean, what is the symmetrical property useful for you? See, it doesn't provide anything.
Yeah.
That means
So
that there's no indication of direction.
It makes the computation simpler, I guess. Because that exactly, because there is like from the way they compute, you can't tell whether they're doing it on a directed or undirected graph. So
well, yeah, that's what I'm saying. All I can see is they assume one direction. They don't make use of the inverse direction and at any point.
Sorry, how are they assuming direction? I don't.
Can you go back to the definition?
It's the IJ, I think.
say they actually don't assume direction.
Yeah, it comes
They
into
don't,
the.
yeah, they actually assume one side direction, right?
How is it?
They only look at outgoing direction, outgoing connection. They don't.
So if there is a nested loop. Did you want to say something?
Yeah, I guess if you have this, I guess the tension of IJ and JI should be different, right? If you have this undirected.
Right.
It's directed.
I mean, because here, right, here they, and of course they should be different. Because
can we have the other way around? Because it's concatenation can be, you know.
Right, but you compute like different.
So it cannot, you know.
You compute them differently.
Can you not interrupt each other?
Sure.
Yeah.
So may I just have a quick comment?
Right.
So if you have a undirected graph, you do this, there's no problem. If you have a directed graph, right, you might want to treat in edges different from out edges, right? You might have, so it might make the algorithm a bit more involved. So that's, but I don't think that it's. I think the authors said that this can be applied to directed graphs as well. There's no restriction, like you said. It's.
What I'm trying to say here is that from here, I don't see why you have to consider incoming connection. Just assuming that you have like directed graph. You can apply the same logic here.
With and ignoring
outgoing.
Yeah.
How do you calculate this attention here? You know, because it's concatenation, and concatenation can be the other way around, right?
But you here from here, I understand that HI is the source node, and HJ is the target node, right? So you are only looking at outward direction. You don't look at backward direction. And if you want to put like backward direction, you would have like WHJ concatenate with WHI in the formula of HI. In the formula for HI, right? Here you don't. And here it specifically says that HI goes before HJ.
But IJ will go through all the nodes. So at some point.
No,
there will be like edges.
yeah, that's what I don't understand. Right, the formula here saying J goes through the nodes of HI, the neighborhoods of HI at the very end.
Right.
So, and the softmax here also sum through OJ. It doesn't have anything to do with I. I here is fixed for each and every node.
I mean, I appears in this alpha and j.
Yeah, but alpha ij is sum over j and normalized over j. It doesn't have to do
Alpha and
anything.
j depends on I from here.
Exactly. Yeah, but that's what I'm saying. For a fixed I, hi always goes first. At least from the formula. So it's directed to me.
So I think the point is there is some directionality only because of that concatenation operation.
Yeah.
Yeah, but of course you can just, this does not necessarily mean out edges or in edges, because you can do the same thing fixed and just flip this the other side. It should just change how you
There is a
compute the
difference
tension
between
vector.
direction or having a directed graph and the order of operations. They are not related in this case.
Yeah, so that's what I'm trying to say here. I mean, at least with this operation, it doesn't force the graph to be undirected. That's what I'm saying.
It's irrelevant to whether it's directed or undirected.
Yeah.
It's just source node and neighbor nodes, but there's no
So
conception.
nothing says that the graph has to be bidirectional.
Yes, right.
For that to work.
No,
So,
I completely agree.
So if there is like an advantage of, I just wonder if there is an advantage of undirected graph.
Okay.
Like internal.
It's more generalizable, I think.
Undirected graph, I thought would be more generalizable. Like for the citation network, it's obviously one, directed.
I'm saying this. I'm saying the same thing.
Yeah, sure.
On undirected graph, I think it's more generalizable.
Yes.
Can I suggest to take this offline?
Yeah.
This
Right.
one.
So, any other points?
Yeah, for back for EIJ and EJI, are they the same or different?
They would be different.
For it is directional.
Yes, they would be different because the attention vector here is fixed, right, for all nodes.
So
And when you flip it, so AIJ and EGI will be different.
so that's, I think that was what he said, right? For it is it's assuming directionality in this case.
Yeah, I think it's unintentional because the author seems to have said that this undirected graph, right?
But
so they have, because of that concatenation operation,
it is directional.
they have some directionality.
No, I mean even if you sweep them, if you like flip them, it's still directional because you only look at the neighborhoods of I, and when you move to Sj, you look at the neighborhoods of Sj. So it's like different, and I don't think that there's going to be the cases when Eij is equal to Eji, mostly.
That's right. You need to note that because it's not required to be undirected. It can be doing as well.
I think the loss function is like kind of dot product of like the learn Zi and Zj to learn A. So it's kind of, finally we hope to have almost the same, I mean, since we are, the intention of that loss function is to have like both attentions the same in either ways, I think A gonna produce the same EIJ, EJI, or at least close.
Okay, I see. So you're saying that the EIJ and EGI will go towards the same.
If the loss function is minimized
Okay,
correctly.
but what if I has like 2 nodes and J has 100 nodes? Then it's difficult to have it. Yes?
I think just because the relationship, when you're looking from one node to the second or from the second to the first, depending on what you're focusing on, just because they are different doesn't mean it's directed, right?
Right.
And I think that's where we're getting stuck, right? Like it matters where you're looking from and where you're looking to, but it's not a notion of directionality at all, like being a directed graph.
That's right.
You had one?
Not on this, if we're gonna.
Right.
Okay. Back to your original discussion point about the question about if you can append an edge feature to a node.
Wait, can I ask one question relative to that before? No, I'm gonna let you go.
Oh.
Yes.
I was thinking about it kind of on the side as we were going through, but I think that breaks down if you increase the filter size to say looking at the next two neighbors. Then you can think of a diamond problem where say you have 3 nodes that in the next step they all go back to the same one.
Yeah.
Then you're kind of stuck, well, you'd have to append 3 edge features to a single node, and then the shapes are going to be different.
So can you go back one slide? Right. So I was talking to Amir about this before, and if WHI and WHJ have to be the same length, then it doesn't totally make sense to append edge information because it only makes sense with respect to one. But do they have to be the same length? Like, could you just add edge features to that vector, and then your A is longer, and it's just...
Yes, they have to be the same length in any way because you want unparted fix. At least
Do you want what to be fixed? Right, but couldn't A just be long enough to incorporate appending like WHI, WHJ, and like a bunch of vector?
Then
vector features.
abstractly, you already increase the size to be equal to some extent, right? Say, if A is 200, then you abstractly you already like restrict HI to 100 and HJ to 100 because really you want first 100 of A to attend to the source node.
Isn't the length the number of features that a node has?
I was thinking
A is 2
an issue with that approach for the inductive learning would be then you'd have to know something about the structure. So you have to put some sort of hard limit on that feature vector.
Yeah, because it creates a relationship between the nodes, right?
Yeah, so you wouldn't 100% know that you wouldn't overflow that feature.
Oh, you don't have the information.
You don't have any structure. It's not needed.
In image processing, if you reach the border of an image, you just do padding. There's nothing special about it.
So that's what you would do here as well? Just keep
But you
increasing?
have to anyway if you have a node that's next to one that you are trying to predict later, right?
So basically, you just pad. Something.
So if you come across...
In transductive learning, you mean?
Inductive.
Inductive learning.
Inductive. Because if you knew the graph, you would know what the max size of that, if you're going to append the edge information.
So is it safe then to say that in the case of transductive learning, you're right, but in the case of inductive learning, you're right?
Unless
you
right
pad.
that you can just keep padding.
Yeah. I feel it's just the difference between transductive learning and inductive learning that catches.
I'm just not sure
the
how
point.
it would work out.
Because in
it transverse through at some point, okay, now we need to...
But in
add more.
transductive learning, you know the structure.
Yeah.
Right?
Inductive,
It's
you know.
inductive, the test is a new graph altogether. Right? So like, which you don't. So I don't know how padding will work on that point, I guess. But for transductive, I really feel as if you were to then what you've proposed, I think that would be sufficient because you know the structure.
So comment about. Comment about neighbor operations, convolutional like operations, is that if you have multiple convolutional layers, right? The receptive field of a node, right? The feature vectors which affect that node increase. So instead of you had a problem defining appending edges to a node feature vector, right? An edge feature vector to a node feature vector, and just using that as an algorithm in a way to use the edges, right? But the nearest neighbor is good enough because if you need the information of a neighbor, you can just do 2 layers, and that node will receive information from nodes that are 2 hops away, and 3 layers 3 hops away, and so forth. So I think it is possible to generalize it to edge feature vectors in a usable way.
What do you want from each edge features? If it's like, because we have this graph that all of the nodes have the same relation to each other, right? They have the same type of relation, right? So if you want to assign a value to it, so the whole point of this attention that we find a weight for that edge, right? So we are just doing all of this problem to find a weight for that, right? So if we already have that weight, so what's the point of going through all this process?
I don't know what the other feature might be, but it's like the number of connections in
Number of connections we already have.
like frequency of conversation between two people in a social network, or like anything that has to do with that.
So that's already the attention that we have. We want to find a way to incorporate the features of this node to other nodes with like a frequency, with a like a weight. So if you already have the weight, so what's the point?
I think that's a little bit different, right? The attention is somewhat you overlook all the network, while the property of an edge is like private between the two nodes.
That's right. Like the number of conversations, example, right? Number of conversations between one person and a social network with another, right? That you can't add to a feature vector. That's really between two nodes.
Multiply it, if it's relevant to multiply to the rate that you already have. So, it depends on the context that you have.
It might not be multiplication.
And that's actually that's one. My point is that my point is
spam by.
I mean, if you don't include that feature in the feature of the node or the edge, if you don't look at the feature of the edge, right now we are saying we discard that feature. How would you learn? How would you multiply? So we are talking about how we incorporate the feature of an edge into the graph. And now, for this structure only, they discard that feature. How often the conversation between the two persons. And if you drop that feature, how do you recover it from the graph that you have, from the attention mechanism that you have?
They don't claim that they can recover such information about the edges. So.
Yeah, so that's what I'm trying to say is that like some of the feature of the edge cannot or should not be overlooked. Maybe.
So it's not applicable to the setting that your edges have features, It's not applicable.
Yes, I understand. Yeah, the point I think her point was that can we incorporate that feature into the structure somehow?
There are several ways to incorporate the structure. Like you're just adding stuff to the edges, you can think it as having, if each edge has like, I don't know, 5 features, you can consider the same as having 5 different graphs, each of them with 1 feature. You can also like think if you want to just consider what happens with the edges, consider the dual graph and play the same game with attention with the dual graph. So there are many different venues where you can add the structure to this thing. So I'm thinking about like maybe wrapping this up a little bit and maybe give the chance to people who haven't asked questions to ask any questions. So like, is someone who hasn't asked any questions or haven't made any comments would like to ask something?
Sorry, this is not related to this paper, but it's just. But yeah, it's just well, kind of a problem that I haven't solved for a long time. In this case, assume that the matrix W is attached to the graph, right?
What do you mean by attached?
That means you have a matrix W for every edge in a graph.
Right.
So in inductive learning, how does it transfer to a graph of entirely different structure?
The matrix W is not attached to the edge of the graph, it's attached to the nodes.
Okay,
so
if it is okay,
W is just an
that's also possible.
prime.
Okay, if it's attached to the node, then how is it being transferred in inductive learning to a different graph, to a graph of an entirely different structure? For example, if the first graph could be linear, and this in inductive learning it is transferred to a grid, and in this case the old W are completely irrelevant. So how does
I think maybe.
How does that
please
happen?
you guys correct me if I'm wrong. Like I think it wouldn't make sense. Like you expect that the data that you're inducting towards is similar to the one that you had before. So you are playing a different game. Like it's like if you are telling me like I have a classifier between dogs and cats, and then you begin giving me images of chickens. It's an unfair game.
But still, they are also 2D images, right? So if they are being casted on a graph, it will still be a grid. So even that case is easier than the case that he described.
You know, Pink, what this essentially do is that you have a graph, and the whole idea of inductive learning is try to somehow embed it to a lower dimension space, right? So when you embed this seen graphs to a lower dimensional space, and then you have this unseen graph.
That's the spectral graph analysis case.
That's give me the overview, right? What's happening in general when you have this inductive learning, right?
Yeah.
So what in here is essentially that when you apply these multiple layers, what you have as the last layer, what is it? It's like an embedding, right? If you think about it. If you have a last layer, it can be interpreted as an embedding.
Yeah. So it's always one-dimensional.
Yeah, but you have embedded the structure of the graph and also the relations into a lower dimension embedding, which is like in the last layer. And then from the last layer, you apply like a softmax or something like that, which helps you to have your classification, right?
Yeah.
So in here, what we do is when we pass the inductive layer, when we have this graph that we don't know nothing about, when we pass it through this network, it will embed it to a space that can help us do the classification.
So before that happened, W is useless.
No, we have trained over the data that we already know about, right? In the inductive learning, we have this graphs, and the graphs, we pass it through it, and then we train the network based on the graphs that we already know, and then we pass the graphs that we don't know nothing about. Then it will provide us with something like an...
Yeah, but on that graph, because you can't set up a one-on-one relationship between the new node and the old node, how do you determine the W without retraining it? In inductive learning, the inference, the graph for inference and the graph training are entirely different. So, after training, every W is attached to a node or edge.
I think
it's attached to a layer.
So every W is not attached to a node, it's attached to a convolutional layer.
Yeah.
So the same W operates on all nodes in the graph. So there's only one W, or if you have, in the simple case, there's only one W per layer. And the same W is applied to every single node in the graph.
Inductive learning is like image object detection. You pass it an image, and then you find something like where is cat or duck, right? Imagine instead of passing an image, you pass a graph to it. That's the way the weights are already trained, you pass the graph. And how you pass the graph? By the adjacency matrix and the node features. These are the representations that you have that which shows you that what this is graph.
The way I see it, inductive learning is more like this. You train it on a lot of time series signals, and you apply it on image. That's
Yeah, I see it more like you train it on a analog box.
Let's keep this for later and let's wrap up. Thanks a lot for coming, and I hope to see you next time. Let's thank the speaker again.